Minimize PowerPoint. Okay. All right. So today we are going to start on part 2, which is going to talk about now what happens when atoms get together. And it's a real simple answer. When atoms get together, they form bonds. They will form some kind of interaction between those atoms. And so we now need to talk a little bit about what can happen to atoms when they get together with other atoms, right? What kind of compounds can be made. So this is about putting atoms together, really to form compounds. And more specifically, we're going to talk about 2 types of compounds, ionic and molecular substances. And to begin with, we will talk about ionic substances. And I'll be reminding you of what makes an ionic compound. We will learn how to name ionic compounds. That's going to take 2 or 3 days because there's a lot of different kinds of naming. You would have learned a little bit about naming in grade 10. You would have talked about things like sodium chloride and maybe even larger ones, something like potassium chlorate. I will be reviewing that with you. And then we'll talk about molecular compounds. We'll draw molecules. We'll even make molecules with molecular sets. And then we'll be ready for a test. This part of the unit is not nearly as long as the first part. So, right, we wrote our test yesterday. We're at the end of week 4, right? We'll be likely writing another test in 2 weeks. So it won't likely take, 4 weeks again. We'll be moving a little quicker. Okay. So don't write this down. Just remember, we talked about matter at the very beginning. Remember, we talked about mixtures, homogeneous and heterogeneous. Really, in this chemistry course, we're not worried about mixtures, all right? We're worried more about the way the substances behave. We have elements, metals, nonmetals, and we just finished our test on the element side of pure substances, all right? We talked about the periodic table and how we break it down. We talked about atoms and how we can determine the number of electrons in the outer shell and all that good stuff. And that's going to become very important. So now, part 2, we want to talk about compounds. Compounds can come in 2 forms, ionic and molecular. Okay, so let's write a little bit down here. Whoops, let me back up, right there. So why do atoms bond together to form chemical compounds? And it really comes down to one common thing. Most chemical compounds want to pair up unpaired electrons. We've seen that, I've made some changes, right? If you've printed them off, you'll be okay. I didn't like the order. I teach it in a slightly different order, but all the same information is there. So why do atoms bond? They want to pair up unpaired electrons. We know how to draw Lewis diagrams. We know how to determine the number of electrons in the outer shell in order to draw it up. And we know that some atoms have paired electrons with some lone electrons, and others have, more lone electrons. What do they want to do? They want to pair up those electrons. They want to achieve a full energy level like the nearest noble gas. We know that noble gases are unreactive. Why? Because they have that full outer shell. And so if an element that doesn't have a full outer shell can gain or share some electrons in order to get a full outer shell, once it does, we say it's stable. It's a stable ion. What is a chemical bond? It's an electrostatic force of attraction that holds atoms and ions together in a compound. Don't judge me. It's my Disney princess's case of chemistry. See? There's chemistry right there. All right. What I have in here is really just a whole bunch of various things that I've taken from my children that they didn't want to play with as children. My son is a computer geek, so he doesn't play with stuff like this. But I bought him all kinds of magnets and other things. What, magnets like this? Yeah, they're awesome, right? Anyway, if I've got a big container of magnets here, which I do, and if I pick that container up, you can see they all kind of clump together a little bit, right? And it's obvious, you guys know the way magnets work. They attract each other, or they'll attract pieces of metal. There's some ball bearings in here, because if you've ever played with these, you can make some really neat structures and that type of thing. But you'll notice it's all kind of stuck together. Now, we could use the term bond to describe the way they're clumping together. We could say that all of this material is being held together by a bond of some sort. The bond, we would say, is a magnetic bond. There's magnetic forces holding those things together. Now, the reason I have a big pile of magnets is because we can easily simulate a chemical bond by looking at magnets. A chemical bond uses what we call the electrostatic force. You've probably seen the electrostatic force in grade 9. Here, I'll show you here some of this equipment here. So here I've got a pith ball, right? Remember the pith balls from grade 9? And I could charge this pith ball. Now, I don't know whether it's going to charge today because it's quite humid out. See if we can transfer a charge. I can't transfer the charge, so it seems to be always attracting, but that's okay. The attraction is a good enough kind of description for what I'm talking about. I can get this electrostatic, it's charged with electricity, this object to attract to that object. You could say that they're attracted together and connected by a bond of some sort. We would say that the bond is an electrostatic bond because it's being attracted because of its electrical charges, okay? This, we could say, is a magnetic bond because it's being attracted because of its magnetic properties. But the way an electrostatic bond and a magnetic bond behave are exactly the same way. They're just attracted by different forces of attraction. One is due to charges, and the other one is due to magnets, all right? So when a chemical bond is formed, you have two atoms that for some reason are attracted to each other, probably because they're charged oppositely, and they stick together. That's what a chemical bond is. All of the molecules that you've learned about and all of the substances that you've learned about in the past stick together or clump together because of the charges within them. That's what makes them sticky. I will often say that atoms are sticky. They tend to clump together. All of the material that we see around us, this desk, right? Our skin, right? The air, not so much. Air particles are not really attracted to each other very much, so they're not very sticky. But all of these substances they have their shape and their form because of this electrostatic force. So, when you are frustrated and try to punch the wall, don't do that, When I was a teenager, it was always some male would be upset, punch the wall. It's just dumb. Anyway, so let's say you do that. The reason you can't push right through the wall with the greatest of ease is because the particles of the wall are being held together by very strong electrostatic forces. They're holding the particles together. So I can't drive my fist through this desk because the electrostatic forces from all the molecules in here are strong. I could drive my fist through some water. Why? Because the electrostatic, isn't that funny? Because the electrostatic forces between the water particles aren't as strong, right? But you can't run through water as easily as you can run through air, right? If you've ever tried running through water, like let's say you're at a pool and you're playing some game of tag, you know the way that works, right? You got to push through the water. You know how you can imagine, it looks something like this. No? Anyway. That's because the water's a little sticky, so you got to wait for the water to go around you. There's electrostatic force. The weakest is for a gas. It's easy to walk through a gas particles because they're not as stuck together, all right? So a chemical bond is due to opposite charges clumping the materials together. Excellent. All right. So let's go back and define compound, remind ourselves about what a compound is. It's a pure substance in which two or more different atoms are joined by a fixed ratio by a chemical bond. And so now we've added the term fixed ratio, which means they only stick together in certain ways. You can't just clump them together anyway. There are only certain ways they can clump together. Put the toys away for today. I'm struggling. Where's one escaping? Can't you see it? Can you see which one's trying to escape? All right, success. This is my Darth Vader lunchbox full of Lego. Also a very important demonstration properties for a chemistry teacher. Two types of compounds exist. Ionic compounds, we're going to talk about that today and on Monday. Then we'll name a bunch of them. And the other type are called molecular compounds. And they can also be these molecular elements. We're going to learn ionic compounds. Actually, you know what? I might even add this underneath. We're going to learn ionic compounds are made up of metal and a non-metal atom put together. So ionic compounds are made of a metal atom put together with a non-metal atom. And molecular compounds are all non-metals. So that's a quick way to identify whether it's ionic or whether it is molecular. The types of atoms that are in there. No need to draw the images, but this is a representation of an ionic solid like salt, sodium chloride, a sodium ion with a chloride ion, and they are repeating sodium, chloride, sodium. Actually, the chloride's the big one. Chloride, sodium, chloride, et cetera, et cetera. Where a molecule is an individual little unit, this represents carbon dioxide, CO2. Okay? So we can have ionic, metal, non-metal. We're going to talk about that today. And we can have molecular, all non-metals, later on down the road. Again, we've got writers on other machines. Can I go ahead? Who's writing, just as a curiosity, who's writing off of the actual slide? 1, 2, just 2, 3. All right, excellent. Just 3 of you. The rest of you are so far ahead. You're also on the slide? All right, were you done? Yeah. Okay. So let's talk a little bit about what is meant by the chemical formula. So a chemical formula is made up of the symbols of the elements that are in that particular compound, and they're also made up of subscripts. That's the smaller number down below, that tell us the number of that particular type of compound. Okay? Yeah, you can let her in the back door there, or she can come into this one. Doesn't make any difference. All right? So in this case, what is this 3 telling me here? Yep. Oh, That's good. Yeah, you gave me even more detail than I wanted. There's 3 magnesium for every 2 nitrogen. But the 3 simply tells me there are 3 magnesium ions in this case. 3 magnesium, and they're technically ions, but I'm going to just write down atoms for now, atoms in this particular substance. And in this case, whoops, the 2, I'll point at the 2 nitrogen atoms. Again, they're actually nitride ions, but we'll get to that in a moment. Are we okay with this idea? That the number tells us the type of atoms that is? Excellent. Let's do a couple of examples here. All right, and then you'll notice that I've got a question sheet counting atoms. Now, I think when Mrs. Murray taught it, she would have then given the sheet. You would have worked for a while. It's obviously on Google Classroom. You can type in those numbers. But I'm going to keep going and finish the note, and then I'll let you work at the end on whatever sheets we've got to work on. So we'll do these examples together, but then I'm not going to give you time right now to work on the sheet. We'll do that a little later on. I like to get through the note and then let you guys work instead of starting and stopping all the time. Easier on my videos too. Now, really, this one's pretty straightforward, and this is the one I want to talk about because it's this number 2 that's kind of special down at the bottom. So for this, let's just go C, and then I'm going to put a dash in here, and an H, I'm going to put a dash in here, and O, and I'm going to put a dash in here. And I want you to tell me how many of those types of atoms there are. Now, on the sheet, you can do that right on, I think, on your phone, because all you'll do is pick the letter and then dash and write down what the number is. I don't think there's a problem. Okay, so how many carbon atoms have we got there, Jess? 12 carbon atoms in this particular thing. How many hydrogen atoms? Conrad? 22. And how many oxygen atoms in here, Isaac? 11. I believe this is glucose, but I'm not sure. It's a molecule of sugar. It has to do with biology. I'm not a biology person. I don't know. Anyway, let's take a look here. The atoms N, H, S, and O are the ones I'm worried about. N, H, S, and O. And we have to be careful about this 2 outside of the brackets. Could somebody tell me what that 2 represents? What does that 2 represent outside of that brackets? Conrad. Sorry, say that again. That's okay. John, you got an idea? Yes. There's 2 of them. Yes. This is an ion, and there's 2 of this thing, which means if I want to figure out how many nitrogens there are in this, what do I have to do? Or what is the answer? How many nitrogen atoms are there in that? Yeah? Yeah. Not 4 by 2. I'm doing the nitrogen atoms. This is the hydrogen atoms. You're right. There's 2 times 4 hydrogen atoms. But how many nitrogen atoms are there? You're right for the hydrogen, but not for the nitrogen. Yep. There's 2. If we don't see a number in a formula, what does that tell us the number is, even though we don't see it? Yep. It's 1. So in this case, you're imagining a 1 in that position. And therefore, for the number of hydrogens, it's the 2 times 1, or 1 times 2. 1 times 2. You can even write that out here if you wanted, just to get yourself straight. 1 times 2, 2. All right, does that make sense? Okay. So then now the hydrogens, there's going to be 4 times 2, because there's 2 of those NH4s. There's going to be, obviously, 8. Now, notice with this SO4, it doesn't have any brackets around it, so I don't need to multiply it by anything. I can just count. What do you got? Yep, 1 sulfur and 4 oxygen. Okay? So the reason I put that example in there is to show you what to do when dealing with brackets. Okay, so that's how we count the atoms. Again, there's a little practice sheet on there. It's not for marks, it's just for practice. But again, I want to keep going. Did you have a question, Conrad? Just stretching there. Awesome. Okay, then let's talk about ionic compounds. So right now we've quickly discussed how we deal with a formula. Let's now go to ionic compounds. Okay, ionic compounds. Thank you. They contain positively charged metal ions and negatively charged non-metal ions held together by what we call an ionic bond. Again, the bond is due to opposite charges. It's still what we call an electrostatic bond. We just call it an ionic bond because it's felt between two ions. So now the next thing we have to do is talk about how ions are formed. How does a metal atom become a metal ion, and how does a non-metal atom become a non-metal ion? All right, that's our next step. Again, I'm never sure. Can I continue? We're good to go? If I jump ahead and you're not ready, just tell me. Formation of ions. An ion is a charged atom which is formed by changing the number of electrons in the valence shell, or the outer shell.
English.
It's just the sound of your fingernails clacking on the keys are a distinct. The nails are nice. The sound is very uniform due to the uniformity of your nails. But the clacking is, I would say, distracting. Yeah. A stable ion has all of its orbits full like the nearest noble gas. So over the next couple of slides, we're going to talk about how atoms can gain or lose electrons and how then they form ions. And then the important thing is, what does the charge become on that ion? Now, if you've printed ahead, all right, or if you're looking ahead, after you get done that one, there's going to be a picture on there of a cation, but I'm going to draw it on. I'm going to draw it on the slide because I want you to see how the how the ions are formed. So if you're writing ahead, when we get to the Bohr diagram thing, just hold off for a minute so that you can see the way I build the pictures. Am I good to go? Anybody? It's terrible. So cations. Let's talk about cations. So there are two types of ions. There's positive ions and there's negative ions. Cations are positive ions. You may wonder where the term cation comes from. It comes from the scientist who originally kind of discovered ions. He did it by using by putting an electrical source in water to see what it did in the solution. And all electrical sources have two parts to them. One's called a cathode and the other one's called an anode. And he discovered that the positive ions migrated to the cathode, and so he called them cations. So they have nothing to do with cats. Sometimes students will call that cations, because T-I-O-N looks like shun. But we pronounce it cation, okay? How do you remember that a cation is positive? I often imagine that the T, if I write it as a little t, it makes a little plus. And then I see it as being a positive. So the T makes me think of the plus. Anyway. Positively charged ion formed when removing electrons from the valence shell until it is empty. The size of the positive charge is equal to the number of electrons which has been removed. Metals tend to lose electrons to form cations. So our guys on the left, group 1, group 2, group 3, they will lose their electrons when it comes to forming a compound. All right? We are going to, but I'm not going to write as much on it. What I've done on my slide is that I deleted all of that, and I'm going to just write it on the slide so you can see the way I draw it. It will be the same atom, but I'm not going to write as much on the bottom because I think it's overkill, a little bit too much. We're good to go? Man, I stand around here. You guys write fast. So I'm going to do an example of sodium, and I'm going to start with a Bohr diagram. So this is the Bohr representation of this. So sodium is going to be the atom I'm starting with. And so how many protons we got in the nucleus here? 11, right? Well, you're looking at the slide. Of course you know the answer. 11. And that's why I want you to not necessarily look at the slide. I want you to see the way I generate this. What's the electron configuration for sodium? You've got the slides printed out too. Okay, all right, that's fair. Go ahead. 2 and 8 and 2, 8, and what are we doing? Sodium? 2, 8, and 1. 2, 8, and 1. 2. Oops! Look at what I've done, and my eraser doesn't work. I'll turn that into a fancy 2. Ooh. 2, 8, and 1. All right? 2, 8, and 1. This thing is going to lose an electron to get to that full outer shell. So in the end, it's going to be 11 protons, and it's just going to be 2 and 8. All right? Okay? Notice this thing has a number of protons, 11, so that's a positive 11 charge. I'll put 11 plus on the back just to write it. This thing has also 11 electrons, 11 negatives. And if I were to add those charges up, what do I get? Nope. What's positive 11 plus negative 11? 0. 0. Therefore, it is neutral. That's what we call a neutral atom. That's a sodium atom. Let's take a look at this situation after it's lost an electron. Number of protons. Yep. 11. Still 11. 11 positive. Number of electrons. Yep. 10. 10 negative. 11 positive plus 10 negative, or 11 positive minus 10. What's it going to be? 1. Plus 1. 1 positive. +1. Don't worry about whether you put the positive before or after. This is a positively charged ion, all right? It is a +1 ion. That is the ion charge, okay? The ion charge. So when you lose one electron, the atom becomes positively charged. Students often make that mistake. They often make the mistake thinking that if you lose an electron, it should be negatively charged. And that's because when you normally lose something, you tend to go down in something. You know what I mean? Let's say you've got a bank account and you spend $10, you give $10 to somebody, your bank account goes down, right? But it's backwards for when you give away a negative charge. When you give away a negative charge, your charge actually becomes positive because you're losing negativeness, if that makes any sense, all right? When I teach the grade 10s who sometimes struggle with this, I try to give them an analogy, and I always tell them to think of hippies when you're thinking of the charge of an ion, right? Because like, let's say, you know, you're a hippie, you'd be saying, you know, you might say, hey man, I don't feel so good, man. And your hippie friend might say, hey man, just don't worry about it. Just push that negative feeling away, man. Just push that negative feeling away as far as you can. And when you do, you're going to feel better, man. You're going to feel positive about yourself if you get rid of that negative feeling, man, right? No? I grew up in the 70s. Does that explain things? So anyway, all right. So I don't know if that'll help you out. Maybe it confuses you. Hopefully it doesn't. If you get rid of a negative electron, it's going to make the atom positive by that many electrons. All right? And see, I'm so confident that I'm going to put that out on the internet. My best hippie impersonation. That's right. Okay, so let's now look at the Lewis symbols. Because you know what? We do not want to be drawing Bohr diagrams over and over again. That's a pain. We don't want to draw all those orbits on the inside. So let's draw the Lewis symbol. So Lewis symbol, Na. How many dots? Yep. I think 1. It's going to get rid of that negative charge, man. Oh, sorry, I couldn't help myself. It's going to get rid of its electron. And in the end, we're going to draw it like this. Na. Yes, it has 2 8, right? But we only draw the outer electrons when it comes to a Lewis diagram. So we've lost the electron and it's gone, okay? Now we need to represent that it's charged. So what we do is we put square brackets around it. That's just what we do when we draw Lewis diagrams. And we put a +1 charge, okay? So it loses the outer electron, and the amount that the positive is the same amount as the number of electrons it's lost. The name of this thing is called a sodium ion. You'll notice that the name stays the same. For the positive ions, the name stays the same. I have a sodium ion or a magnesium ion or an aluminum ion. It's for the negative ones where they get the "ide" ending, like a chloride ion. But the positive ones, the name stays the same. All right? Let's do another example here. Let's just put here example 2. And let's do a magnesium, or let's do calcium, Ca. How many dots? Yep, 2 dots. 2 dots. It's going to lose them all because it gets rid of all of the dots. John, you're looking for calcium. You see it? It's in group 2. 2. Just was wondering if you seem to be glaring there. We're going to lose 2 dots. We put our square brackets because it's lost those dots. And what charge will our calcium ion become? What charge will it become? Yep, Bethany? +2. +2. Excellent. Nice. You didn't say it like a hippie, but that's okay. That's all right. Oh, and what would the name of this ion be? Yep. Calcium ion. Calcium ion. Excellent. I could do the same for aluminum. For silicon, we're now into the nonmetals, and that's something else. we'll deal with that in a moment. All right, nice. So again, at this point, there is a sheet that you can do. And again, I want to finish the note and then get you working on things. So I'm going to talk about negative ions, and then I'll get you working on the sheets. All right? Sorry? You will do it eventually, but it's, the sheet is on your, actually, you know what? Maybe we will work for a while. I'll stop here at cations, and we will work on that. So I'm going to stop the video. We're going to go to the Google Classroom. We're going to get the sheets out, and then I'll let you work for a little bit. And if I don't get to the negative ions, I'll get to that on Monday. We'll see how that goes. Because if I go too far, you'll have too many things maybe confused. So let me shut this down, and then I'll bring up Google Classroom. You can already go to Google Classroom.